Today I will be speaking about determining the available phosphorus release for Natuphos E 5000G phytase for nursery pigs. Phytase is an enzyme that's commonly added into swine diets, and it's done such to help release the phosphorus that's bound up in the form of phytate in common cereal grains and oilseeds and make it available to the pig. As we do this, we're able to reduce the amount of inorganic phosphorus added into the diet and help reduce the phosphorus that's excreted by the pig. How phytase works is that it catalyzes the stepwise removal of phosphates from phytate or phytic acid. Now, as manufacturers continue to improve the efficacy of the enzyme, we need to keep evaluating each new source. So, as these new generations become available to the marketplace, new phosphorus release curves need to be conducted in order to determine how much value each source of phytase has, thus how much available phosphorus a certain amount of FTUs will give in the feed. Typically, phosphorus release curves are derived from measuring the response criteria of average daily gain, feed efficiency, and bone ash values. Thus, the objectives of the present study were to evaluate the effects of a novel phytase source, this being Natuphos E 5000G from BASF, on nursery pig performance and bone ash values. Secondly, we aim to develop an available phosphorus release curve for this specific product. In this study, we used a total of 286 nursery pigs, initially weighing 11 kilograms and being 40 days of age. They were used in a 3-week growth trial. Pigs were randomly allotted to pens at weaning, and then on day 18 after weaning, pens of pigs were randomly allotted to one of the 8 dietary treatments. There were 4 pigs per pen and 9 pens per dietary treatment. All pigs were fed the control diet, which was 0.12% available phosphorus for 4 days prior to initiation of the experimental treatments. Pigs and feeders were also weighed every 7 days to track growth performance and feed intake. Treatments in this experiment were set up to perform a slope ratio assay with inorganic phosphorus being the control phosphorus source. In this case, we used 21% monocalcium phosphate. The control slope consisted of 3 different diets. The first was the control at 0.12% available phosphorus. The second was the control, so 0.12, plus an additional 0.06 for a final of 0.18% available phosphorus. And the third was 0.12, our control, plus an additional 0.12 for a final of 0.24% available phosphorus from the inorganic phosphorus source. The next 5 diets are going to make up the experimental slope. Again, we have the control formulated at 0.12% available phosphorus plus the addition of increasing concentrations of phytase from 150 up to 1,000 FTUs per kilogram. In this study, for feed manufacturing, all ingredients that contained calcium and phosphorus were analyzed prior to formulation so that we could determine the correct nutrient loadings. Additionally, we used the analyzed phytase activity in order to establish proper phytase inclusion into each of the experimental diets. All diets were then derived from 10 identical basal batches to help reduce the variation that can be seen from different batches of feed. We took a subset of bags from each of these basal batches and then used them as the major ingredient in each of the experimental diets. Additionally, we hand-added treatment-specific ingredients to achieve our final dietary treatments. This next table shows the composition of the basal batch on an as-fed basis. You'll notice that it's a standard corn and soybean meal diet fed to a phase 3 nursery pig, formulated at an SID lysine of 1.25%. Additionally, I'd like to note that the available phosphorus was formulated at that of negative control, being 0.12%, and then we added limestone or monocalcium phosphate to achieve the calcium and phosphorus concentrations in our control diets. This next table shows the experimental composition on an as-fed basis. First, we'll look at the first 3 columns, again, which are going to make up our control slope. We have the increasing amount of available phosphorus from 0.12 to 0.24%. Like I mentioned before, limestone or monocalcium phosphate were added to the diet to increase the calcium and phosphorus concentrations in this experiment. Additionally, sand was added as a non-nutritive ingredient across all experimental diets, such that the same amount of basal mix could be maintained in all of the experimental diets. For the phytase diets, you will notice that we increase the concentration of phytase to achieve the proper levels used for this experiment from 150 up to 1,000 FTUs. Now, the second half of this table shows the analyzed composition of each of these diets. What you'll notice here is that the phytase concentrations analyzed slightly higher than we had formulated for. However, they still increase in a stepwise fashion. At the end of this study, on day 21, 1 pig per pen was euthanized via captive bolt. From these pigs, we collected the fibulas so that we could determine percentage bone ash. For bone analysis, all cartilage caps were removed from the fibulas, and then the bones were boiled for 60 minutes so that we could remove any adhering tissue. After this point, they were dried for 7 days in an oven, and then they were placed in a muffle furnace for 24 hours for ashing. After that point, we were able to calculate total ash weight and percentage bone ash. Data analysis in this experiment used the Proclimics procedure of ASAS. PIN was used as the experimental unit with linear and quadratic contrast statements for increasing inorganic phosphorus or increasing phytase concentrations. Significance was set at p is less than 0.05 with tendencies at p is less than 0.10. As we move on to the results portion, first I'd like to set up my slides. Along the vertical axis, we have the response variable, in this case, average daily gain in grams. Along the horizontal axis, we will have the dietary treatments used in this experiment. The first 3 would be increasing available phosphorus from our inorganic phosphorus source. The next 5, or the green bars, would be the increasing concentrations of phytase, or Natuphos E 5000G. I'd also like to note that the red bar, or 0.12% available phosphorus, was used as the zero inclusion in the phytase contrast statement. This was done because if you can remember back to formulation of these diets, the 0.12% was used as the control, and from there, we added the increasing levels of phytase to that diet. So it was a good comparison to make. For average daily gain, as we increased available phosphorus in the inorganic phosphorus diets, we observed a linear increase in average daily gain. As we increased Natuphos E from zero inclusion up to 1,000 FTUs, again, we observed a linear increase in average daily gain up to the highest level of phytase. For average daily feed intake, within the control diets, increasing available phosphorus from 0.12 to 0.24 increased feed intake among the pigs. Additionally, increasing phytase from 0 up to 1,000 FTUs linearly increase average daily feed intake. Similar to the previous 2 slides, as we increase available phosphorus, we see a linear improvement in feed efficiency up to the highest inclusion of available phosphorus at 0.24%. Now, as we increase the phytase in the diet from 0 all the way up to 1,000 FTUs, we observe a linear increase in feed efficiency up to 590 grams per kilogram among these pigs. Now, the next 2 slides are going to show the fibula ash data, and first, we will look at fibula ash weight. Similar to what we observed in the growth performance of these pigs, as available phosphorus increases in the diets, we observed a linear increase in fibula ash weight. Additionally, as we increase the phytase inclusion from 0 up to 1,000 FTUs per kilogram, we observed a linear increase in fibula ash weight amongst these pigs. Finally, fibula bone ash on a percentage basis, similar to the previous slide, as available phosphorus increases in the diet, we observe a linear increase from 38 to 42%. Now, as we increase phytase in the diet from 0 up to 1,000 FTUs, we again observe a linear increase in fibula ash weight from 38% all the way up to 45% fibula bone ash. Now, if you'll recall back to the beginning, our second objective was to develop an available phosphorus release curve for this particular product. How we did this is using simple regression. We created a slope and intercept using the control source, and then using those coefficients, we put them into a model so that we could determine what the available phosphorus release would be for each of the increasing concentrations of Natuphos E. This next slide shows the available phosphorus release for Natuphos E when we use percentage bone ash as the response criteria. What we have here is the available phosphorus release on the y-axis and then the increasing concentrations of phytase on the x-axis. Additionally, you will notice that we have each of the pen means represented with a blue dot, so 9 per treatment. When we fit a line to this model, we discovered that using regression, we can predict the available phosphorus release using the equation of 0.000212 times the phytase inclusion in the diet. This would range anywhere from 0 at 0 inclusion in the diet up to 0.22% at 1,000 FTUs. In conclusion, we were able to develop an available phosphorus release curve for Natuphos E 5000G when it's included in nursery swine diets between 150 and 1,000 FTUs per kilogram. Additionally, release values for this particular experiment range from 0 up to 0.22% available phosphorus at the inclusion of 1,000 FTUs per kilogram, and it can be predicted using this equation. With that, I'd like to give BASF a thank you for partial funding of this product, and thank you for listening.